Welcome. This video is going to talk about the 5 basic types of chemical reactions that many chemical equations or reactions can be classified as. And as it says, some reaction doesn't fit any of these 5 types, or it fits more than one kind of the 5 types. But we're going to keep it simple and just focus on the 5 basic types, which are synthesis, decomposition, combustion, and then single replacement and double replacement, or sometimes they're called single displacement and double displacement. Either way you want to think of it, displacing or replacing, same thing. So synthesis is when 2 or more reactants combine to form one product, and we can represent it by saying A plus B yields compound AB. Or an example of this would be 2 hydrogen molecules will combine with 1 oxygen molecule to form 2 water molecules. Decomposition is then the opposite process or reaction when a single compound breaks apart to form 2 or more products. So it's represented by compound AB decomposing into element A and element B. So an example would be just the reverse of what we looked at. If you have 2 water molecules and they decompose or break apart into 2 hydrogen molecules and 1 oxygen molecule. Combustion is defined as oxygen gas combining with another reactant to make products along with either heat or light or both being emitted. So combustion reactions often fit another reaction type. Synthesis or single replacement are often the case. Hydrocarbons are commonly part of combustion reactions, and a hydrocarbon is a compound with only hydrogen and carbon in it, and they always produce the same 2 products, CO2 and H2O. So these are equations that we see commonly in our examples that we work. So a combustion reaction can be represented by A plus O2 will yield B plus C plus heat or light. And heat or light may or may not be included on the product side because technically heat and light are energy, so they're not matter. So they may or may not be included. But the one thing that has to be included is on the reactant side, you have to see oxygen in its elemental form, the diatomic gas, being combined with another product. Single replacement reactions then, a single element replaces an element that's in a compound. A metal has to replace a metal in a compound, and a nonmetal has to replace a nonmetal in a compound. That's because when you have metals and nonmetals in a compound, remember they're ionic compounds, and the metals are losing electrons and the nonmetals are gaining. So a nonmetal can't suddenly lose electrons to replace a metal, just like a metal can't suddenly gain the electrons to replace a nonmetal. So only metals will replace metals, nonmetals will replace nonmetals. So we could represent it as A plus BC would give you B plus AC. In this case, I can tell that A and B must be metals because they're the first thing in the compound. If it was a nonmetal, then A plus BC could give me C plus BA, and in this case, A and C are nonmetals and found at the end of the compound. So I've given you an example of each. Magnesium plus sodium chloride can give you sodium plus magnesium chloride. Also, fluorine glass plus sodium chloride could give you sodium fluoride plus chlorine gas. Double replacement reactions then are the last reaction to talk about. It's an element of one ionic compound replacing an element in another ionic compound. And the metal cations can trade places, or the nonmetal anions can trade places. But the cation cannot trade places with the anion. In other words, a metal cannot trade places with a nonmetal. So this is if you have 2 couples dancing and they trade places versus single replacement where you just have 1 couple dancing and someone comes and cuts in. And with double replacement reactions, it always starts with 2 aqueous solutions, and then the products are always 1 aqueous solution plus either a precipitate, which remember is a solid, a gas, or water, which at room temperature is a liquid state. So basically, you're going to form a solid, liquid, or gas along with the aqueous solution. Now, the solid is easy to see, and the gas will bubble and easy to see. The water isn't so easy to see. So just the fact that it remains liquid is your hint that water was produced. So it's represented by AB plus CD gives you AD and CB. So in the way I've drawn it, you maybe are thinking that the anions traded places. I could have just as easily written CB first and AD second, because just like math, the order doesn't matter. It's the same two products. And then you maybe would think, oh, well, the cations switch places. Really doesn't matter which way you think of it. They're trading partners. So I have an example here. Lead iodide plus potassium nitrate will form lead nitrate and potassium iodide. And again, you can see I started with two aqueous solutions, and I still have one aqueous solution, but this Ki is going to form a solid or precipitate, and we'd be able to separate it from the liquid lead nitrate when we got finished. The other thing to talk about is something called a metal activity series. How do you know if these react or not? Not everything reacts when you put it together. So metals are ranked by their reactivity to each other, and this has been done experimentally. They simply put the things together and see if they react or not. So there's a list, and you can find this list in your book. You can Google metal activity series. You can find this list pretty much anywhere in today's electronic age. But the most reactive metals are put at the top of the list, which means these metals will lose their electrons easily. Now, the key here is that it's the metal. It's the solid elemental metal that's going to react and lose its electrons easily. The bottom of the list is going to be the least reactive metals. And you maybe haven't thought about this, but these are things like gold, silver, and copper, which are highly prized because they don't react. Okay, so those metals hang on to their electrons more tightly. In other words, they remain metals. So it can be used to predict if a single replacement reaction will occur. Predicting double replacement is a little more complicated. But with single replacement, a more reactive metal will react with the less reactive metal ion. There's also a halogen activity series, so that's just comparing the halogens in group 7A. Fluorine, chlorine, bromine, and iodine. So if we take a look at, I've got two triads here for you. In the first triad, I simply want you to see if you can identify each type of reaction. And you might have to scroll back through the notes and look at my hints for it. But go ahead and pause and see if you can come up with a guess for each of these, and I'll start writing in my solutions. So I start with one reactant. I end up with two products. That would be considered decomposition. In the second one, I have two reactants and two products. And if I look, I see that partners have changed, so this would be considered a double replacement or double displacement if you prefer. My third one, I have two reactants and two products. And this one, isn't quite a single replacement because the oxygen, even though it seems to have replaced it, it's replaced it with both. The oxygen ends up with the sulfur, but it also ends up with the carbon. So this is going to be a combustion reaction. It fits the criteria for combustion because it has O2 as a reactant. And in this case, heat and light weren't listed as a product, but they don't need to be listed since they're energy sources. In my fourth example, I've got two reactants combining to form one product, and that's called synthesis. And my last example, this one is a single replacement, although it might be a little bit tricky for you to see why it's a single replacement. But you've got Li and H2O. You can really think of H2O as being H plus with OH minus, or HOH. And if you think of it that way, you can see that the Li bumped the H off, leaving me LiOH and H2 as the single element. My second triad, I want you to see if you can predict if each reaction will occur based on the reactivity series. So you'll have to find a reactivity series, either Google it and pull one up or get to your book. And if the reaction will take place, go ahead and complete the equation. So with Ag, silver metal, plus copper nitrate, what I need to know is this metal more reactive than copper? And the answer is no. So this reaction will not take place. NR, no reaction. In my second example, I've got cobalt with silver nitrate, and if you look on a reactivity series, cobalt is more reactive metal than silver. So the cobalt is going to bump the silver off, and now I have to make sure I look at my oxidation numbers. Cobalt, I'm going to assume it's up oxidation number of 2 because I don't have information contrary to that, so we'll go with it. So that means it's going to form CONO3 parentheses 2, and silver, like any other metal, will just be monoatomic. F2 plus HCl. So the question is the halogen, the elemental halogen, more reactive than the halogen ion? And the answer is yes. Fluorine is the most reactive of all nonmetals. And so it is going to form HF. And then that is going to leave diatomic chlorine gas, or Cl2. And if I balance this, I would simply need a 2 there. And I realized I didn't balance the one before. I would need a 2 here and a 2 here to complete the balancing. One thing you'll notice is single replacement and double replacement reactions tend to balance quite easily. It's the decomposition and synthesis that can get a little messy. And then my last one, I've got Br2 with HCl. So the question is Br2 more reactive than HCl, or more reactive than the Cl specifically? And the answer is no. So again, there would be no reaction with that one.